Hello everyone, welcome to the second session of D and F block element. In this session, we will be talking about physical properties. We will be also looking into atomic and ionic sizes and oxidation state of D block elements. So let's begin. So physical property. So first thing, we should go through their structures. So you can see this is your 3D series, this here is your 4D series, and this here is your 5D series. So you can see that is HCP, BCC, HCP, BCC, BCC, all these structures. Okay, so we know what is HCP. Okay, HCP is hexagonal closed pack. Same way BCC is body centered cubic. Okay, X is actually a typical metal structure. Okay, so these are known from solid state. No need to remember any of these, but you should know what is HCP, what is BCC and all. Okay, also there is a CCP. CCP is cubic closed pack structure. So these are different lattice structures of the transition element. No need to remember, I repeat. Then so nearly all the transition metals, since we have seen that they have all the HCP, BCC, FCC type of structure, so all of them, they are in solid state. So hence they are all in solid state and they have high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. So electrical and thermal conductivity comes because of the electrons which are present in them. Now another thing is transition elements, of course exception of Zn, Cd, Hg. Okay, they are very hard and have very low volatility. Okay, that means they do not go in gaseous form easily. Also their melting and boiling points are quite high. Now the reason for having high melting point is because they have greater number of electrons from n minus 1d orbital, okay, apart from ns. So that's why they have more number of electron which help them to do interatomic metallic bonding. Okay, that's the reason. Now I will show you the trend first. So if you see, this is the trend. So the trend says that the melting point rises up with some exceptions, of course, and then it falls down. So rises up and then it falls down with some exceptions. Again, here you can see third series, it rises up and then falls down. So in a row, the melting point of the element rises to a maximum at D5. Then except for some anomalies of Mn and Tc, which we have seen, they fall down. Okay, that is, as you go ahead it increases the melting point and then it decreases. Now in general, greater the number of valence electron, stronger is interatomic bonding. Okay, so if you see electrons are more and then again they decrease, basically pairing is being done, so it goes up and then it decreases. Same way you can see in this case also we are talking about delta H. Okay, so that is delta H naught of A, that which is atomization. So these are enthalpies of atomization. That means when you want to remove one single atom from the structure. Okay, so you can see again the same trend is being followed, that is it increases to the middle and then it again decreases, increases and then again decreases. So you can see this is your series 1, that is 3D, 4D and 5D series. So the metals of the second and the third series, that is blue and the red curve, they have greater enthalpies of atomization corresponding to series first series, that's 3D. Okay, so this is one observation that you should have a note of it. Now next, yeah, also you can see that this is an important factor in accounting for the occurrence of much more metal-metal bonding in compounds of heavy transition elements. So all of them, since they require more energy, they have more frequent metal-metal bonding. Now talking about the atomic and ionic sizes, okay, as you go along a period, the atomic size decreases. Okay, now here there is another thing that you should know. Okay, what is happening is shielding effect of d orbital electrons, and that is actually not effective. Okay, so that is basically, let me explain with the help of a diagram. Let's say that we have the nucleus here at the center, which is a center of positive charge. You have your valence orbital, that is the outermost shell, valence shell. Then we have inner orbital, and then we have even more inner orbital, that is, let's say, ns. Then we have last but one, that is numultimate shell, and then we have anti-numultimate shell, okay, that is n-2 f orbital. So because of this orbital, f orbital, if the electron comes, the last electron in f orbital, if come, it comes in this. Okay. So if you see, the last electron are there, and it is not able to shield the outermost electron, because note that electron and electron, they will repel from each other. But this electron, due to so much large distance between them, it's not able to shield the outermost electron. Okay, so hence the size is even further reduced. So this is actually also known as lanthanoid contraction, because we are filling f orbital, and that is 4f or 5f. So in general, lanthanoid contraction, that is for lanthanoids, and actinoid contraction for actinoids. So an increase from first 3D to 4D series of the element, but the radii of the 5D series are very much same as compared to the 4D series. So there is first increase from 3D to 4D. Let me show you the trend also, then you will understand. So if you see these, this is the trend. Overall, the trend is decreasing trend. Okay, but as you see, the second series and the third series, they have very much similar radii. Okay, the reason is between these two series there is the lanthanoid contraction which is taking place. Before filling up of 5f, you have to fill before filling 5d orbital, sorry, you have to fill 4f orbital, that is your lanthanoid. So between these two series, 4d and 5d series, you have the lanthanoids. So because of that, what is happening, lanthanoids are actually contracting. Okay, that is due to the poor shielding effect of d orbital electron, or let's say in this case shielding effect of 5f orbital. Okay, so as a result of lanthanoid contraction, we note that they have the second and the third D series, they exhibit similar radii. For example, ZR is having 160 picometer and HF is 159 picometer. So you can see ZR and HF. So ZR and HF are having very similar radii. Okay. Also, as a result of this, we know as you go ahead in the periodic table or along a period, the atomic number increases. As the atomic number increases, atomic mass also increases. And we see that volume, the radii is decreasing. So if radii is decreasing, volume is also decreasing. So as a result of all this, as a combination of these two factors, the density of the element is actually having an increasing trend along a period. Okay, so this is one graph, we will see it again. Next, ionization enthalpies. So since we know that the size is decreasing, okay, and there is again poor shielding effect, and the nuclei is able to attract the last electron much more closer. So what we will see, the trend will be an increase in ionization enthalpy, okay, along each series of the transition element from left to right. Meaning, as you go along a period, you need more energy to remove an electron. Okay. In all these transition element, we have the lowest common oxidation state, which is +2. So ionization enthalpy, again, let me just highlight that ionization enthalpy is the amount of energy required to remove an electron from an isolated gaseous atom. Now, going into oxidation state, as I said in the previous slide, that the lowest common oxidation state is +2. Okay, so you can see they exhibit multiple oxidation state. You can see, for example, vanadium is +2, +3, +4, +5. Chromium is going from +2 to +6. So all these oxidation states are seen. Also Mn, okay, you can see iron +2, +3, +4, +6. So the bold ones, the highlighted one, are the most common ones, okay, that are kind of exhibited by the element. So these are all the oxidation state that they exhibit. Note down, Mn exhibit from +2 to +7. That's kind of the highest oxidation state. Okay, some comment. So in group 6, MO4 and W5. So MO is molybdenum and W is tungsten. So you see this 4, this 6. Okay, so this 6 is actually the Roman number 6, which represents the oxidation state. Okay, if you write the element and write a Roman number like this, it represents the oxidation state. Okay, so these are actually found to be more stable than Cr6. Okay, you can see Cr, Mo, W, they are actually in the same group. Okay, that is your group 6. Then because of all this, Cr6 in the form of dichromate in acidic medium is a strong oxidizing agent. Okay, whereas MoO3 and WO3 are not. So that's the consequence. Then the low oxidation state are actually found when the complex compound has ligand capable of pi acceptor character in addition to sigma bonding. So this part I am not discussing here. We will see such type of diagram in the next chapter, that is coordination complex. So you can see this is your metal here. So these are kind of molecular orbitals of the metal, and this side you have your ligands. Okay, and this is kind of the splitting of the energy. That's kind of bonding and anti-bonding. If you remember, when we were dealing with chemical bonding, we were seeing some sigma and sigma star. So something similar is seen here. You can see Eg star, T2G star. Okay, T2G I don't see, T1U star. Okay, so now we will not go into detail, but in the next chapter we will go in little bit more detail. So some of the examples you can see, NiCO4 and FeCO5. So these are some of the example of low oxidation state. Okay, in both these cases you see that nickel and iron, they are actually neutral. They have their oxidation state equals to 0. Okay, next. So trend and stability of higher oxidation state. Now note that Cu2 plus aqueous form as when it's compared to Cu plus aqueous form. So Cu2 plus is more stable, okay, as compared to Cu plus aqueous. The reason is because of more negative hydration enthalpy. Okay, so when you put them in water, they are surrounded by water molecule, and Cu2 plus is giving more amount of energy, and hence Cu2 plus is more stable as compared to Cu. Okay. Also, the ability of oxygen to stabilize high oxidation state exceeds that of fluorine. Note that fluorine is the most electronegative element, but yet it is not able to stabilize. Okay, so oxygen is having, let's say, higher power, okay, or higher authority as compared to fluorine. Also note that the ability of oxygen is to form multiple bonds to metal explains its superiority, because oxygen here can form two bonds, okay, and fluorine can form only one bond, because fluorine's oxidation state is -1 only, whereas oxidation state is -2. So you can see these are the oxidation states. So +1, +2, +3, +4. These are group 3, 4, 5 and up to 12. So you can see the fluorine one is going up to +6, CrF6. Okay, so this is the highest oxidation state. Also note that Mn is going from let's say with fluorine it goes maximum up to 4. Okay, because it cannot bond furthermore. Whereas in with the help of oxygen, or in case of oxygen, it is able to form a compound that is having oxidation number +7. So Mn is having +7 oxidation state in Mn2O7. Okay, so hence oxygen has higher superiority. We will talk about this compound in the coming sessions. So just have a note from this part, it goes up to +6, but when I talk about compounds made with the help of oxygen, it goes from let's say +1 to +7. So that is oxygen is superior as compared to fluorine. And that's it. Okay, so see you in the next session. Bye bye.